So here we are with the second of the NMR. This time it's carbon-13 and we're looking at the spectra of those. But we're joined by some special guests today. Here's one of them. As if on cue, thank you so much. This is Deaky. We're going to get on with the video. After we've had a look at, oh no, you see there's more than one. This is Geddy, and it seems not to be speaking on cue. Thank you very much. Yeah, cutest video of the lot so far. Carbon-13 NMR. As a counterpoint to that, this is going to be get your brain in gear time. We need to be talking about interpreting the spectra. Yeah, I'll be quite distracted. The catkins on the floor. So we need to get in our heads a number of things. The first thing is what is called a TMS reference. TMS reference is the 0 point on the ppm scale that everything is compared to. Now this is TMS. It has TMS is an abbreviation of its name.
Stands for this.
It's one word. I didn't leave enough space to write it as one word. Tetramethylsilane. Silane meaning SiH4. Replace the hydrogens with methyl groups. And it's used in both carbon-13 and proton NMR because it has a strong signal because of because of its structure. It has 4 identical carbons, so it absorbs fairly strongly, which means you can use a very tiny amount of it in the sample that goes into the NMR machine. So it has 4 identical carbons, but of course if you're using it for proton NMR it has 12 identical hydrogens, which again is a useful reference point. And those are fixed, whether you're doing carbon-13 or whether you're doing proton, they are fixed as the 0 point. So when you look at an NMR spectrum, you'll find the 0 is there, and you may have noticed on the previous video when I did it, I did a little line at 0. This, which obviously I didn't mention then, is the TMS marker. So tetramethylsilane, and then chemical shift, and it'll be in ppm. Now, if you're doing carbon-13, the ppm values are larger. They go up to, if it's ppm for carbon-13, it goes up to around about 240 on that scale. If you're doing proton NMR, it goes up to 12 because the energies differences are much smaller. Now really what is happening is, this is a very high energy, I mean none of it is particularly high, it's all radio waves, but this is the high energy end. And everything within other molecules is less energy. So therefore that's why the scale goes that way. So it's ppm less than TMS. And you might get something like that. There you go. That one there represents 2 and that one represents 1. So if that one's twice the height of that one, I can't say I measured it, I just did it by eye. And I'm quite close to the board, but it would mean that there were 3 carbons in that molecule. We need to start looking at environments, because environments is the key to what NMR is going to tell you about the molecule. Why do we do NMR? Well, it really is involved in working out, by using a deductive detective skills, what an unknown substance is. Don't just get NMR, it comes in a question with a whole load of other things. I may have said that similar thing earlier on different videos, where you might get mass spectroscopy, you might get infrared, and then you'll get some NMR and you get the question, what is the substance? So NMR, understanding it is key to solving the identity of an unknown. I need to get some stuff on the board ready for doing our first looking at what's going on about environments. I'll see you after the edit. So, no, I can't concentrate either. Hang on. Oh, ripping my neck. So, environments. Hurty neck. First one, methane. Obviously, with only one carbon, there was only one environment. Not likely to be a question you'll get. Ethane, because the CH3 is attached to a CH3, and if you do it, you go from the other direction, it's still CH3 attached to CH3. One environment again. Now here, the two carbons on the end are the same when you look at what it's attached to. Each one of them is attached to the central CH2. So that would mean the central one will be different, not massively different. The shift won't be hugely far from each other. So it will be a 2-to-1 ratio, because there is 2 in environment A where CH3 on both ends of the molecule is attached to the same central CH2. The CH2 in the centre is attached to 2 CH3s. That makes it different, and therefore it's a different environment, slightly different chemical shift, and that will show in an NMR spectrum. But at the moment we're just trying to spot environments. So when we look at this, we mentioned this one earlier, this is the ethanol from the other video. It has 2 environments. I didn't put that has 2 environments. This one has 2 environments as well. But we just need to start looking at what the environments are. Now you are going to have to use the NMR interpretation content of your data booklet, data sheet, whatever it's called, and it will have chemical shift values. What you find is that a particular structure within a molecule has a fairly small ppm range that you will find it in, and therefore you can identify it as, oh, that shift means this. So they do overlap, so there's a bit of insecurity in your decision, but usually with the other information in the question it's fairly clear what it is. So when you look at this carbon here with a dot on it is this one here, and it is attached to some other R group with carbons. So that's that one. This one, which I put an asterisk on, is that one. So it's got an R group which is represented in CH3, and it's attached to a single bond to an oxygen on the other side. So 2 different environments, and this will have a higher energy transition because it is going to be nearer to the TMS, and this one will be further away from the TMS. And you may recall I said there were 2 different ones in the previous video. 1 carbon in each, so the ratio in that will be 1-to-1. At any point, pause this video, make your notes, go back over it, check that you've got it right, because it's absolutely critical that you understand environments. My neck is now stinging from the little attack earlier. Here is ethanoic acid. Ethanoic acid, only 2 carbons. There are 2 environments because those carbons are not in the same situation or environment. Carbon A is CH3 attached to a, what we call that, a carbonyl. So carbon A is that one. That'll be a much higher energy shift nearer the TMS than this one. It's all about the electrons around the carbon and whether they've been pulled away by electronegative atoms like oxygen. So this oxygen has pulled electrons away, unshielded the nucleus, and the magnet is easier to flip. But you don't need to know all of that. So B represents a carbonyl. Now that could be anything there, there's a number of things that could be, you know, that kind of thing could be an aldehyde, could be an ester, could be, but it represents that arrangement. When we get to this here, butylamine, or what's the 1-aminobutane is another name people use for it. There are 4 environments. Now you might look at that and go, aren't the CH2s the same? No, because you have to look what's either side of it. Is it exactly the same? If it's exactly the same, I agree, it's, you know, it's repetition. But it's not like that. Down there. So the one on the end, carbon A, is attached to CH2CH2NH2. Carbon B, CH3 on one side, CH2CH2NH2. Now carbon C, similar but not exactly the same. So they will come up slightly different ppm values, slightly different chemical shifts, B and C. In fact, A, B and C will be fairly similar in chemical shift. And then that D, where it's attached directly to the NH2, that'll be a distinctly separated, and in fact it'll be a lower energy one where it's further over to the left. So you will see 4 environments there. Let me put that was 2 earlier, but there we go. Right, so when you look at those, these are the numbers of the environments so far. At the bottom of the board, cyclobutane, C4H8. How many environments? Have a little think. And have you thought how many environments? They're all the same. Every way you go around that, you get the same sequence of carbons. It's one environment. Here's cyclohexane, done as a skeletal formula. Again, short time to think. How many is it going to be? How many is it? Same answer. It's 1. All those carbons are identical. Now we need to move on to getting a little bit more into the looking at the spectra and what it will be, but I need to get the board ready for that. I will see you in just a moment. Yep, more distractions. There we go. So what would the NMR spectra for some of those things we've just looked at the environments look like? Well, here's the first 3. Methane, single environment. This is the chemical shift value. Now in an actual question, it's likely you'll have to read it off on the scale rather than be told the exact value. 2.3 generated out of a computer because it's more accurate than using your eyes. It would just be a 1 peak. What's this peak at 0? Let me hear you all say those 3 magic letters. Not going to mention it every time, but that's the TMS peak. You do get questions about why TMS is used in either multiple choice, I see it in multiple choice questions sometimes, but often it's a single point thing about what is the reference or what's the TMS for, it's a reference. When you look at the next one, ethane, slightly further over, but on a scale it goes up to 240 for carbon-13 NMR. That's not a massive shift that way from 2.3. The scales along the bottom are just not the same. I mean, I'm just sketching them out. So TMS again, it's twice the height. Why is it twice the height? Because there's 2 carbons of an identical environment absorbing, so the peak will be twice the size. Little thing about the peaks are not straight lines. When you look very closely at an NMR spectrum, and it's quite hard to draw there on the board. I'm going to get in front of the board just to see. They actually look like that. They are very sharply pointed triangular peaks. And the way that you determine how many carbons it represents is the computer that deals with the results and produces the printout analyses the area of that triangle. It's not a very difficult calculation, area of a triangle, and the area, but it's a really narrow triangle, so when you look at it, it almost looks like a vertical straight line. And so for the simplistic purposes of what I'm doing, because my artistic skills are limited, I just draw them as a straight line, but in fact they are up and down, very tight. It's like a stiletto blade, you know, really fine and sharp. Now when we get on to propane, which we said there were 2 fairly similar environments, here they are at 15.8 and 16.3. You would be distinctly able to identify that firstly they are next to each other but not at exactly the same chemical shift, and you would be able to clearly see that one is twice the height of the other, or it would tell you that one is twice the height of the other with a little marker saying how many, it's called integration, area under this is called integration. So forward planning, run out board. Integration of the area. It will sometimes tell you the integration, sometimes you just have to look at it and go, oh, it's twice the height. Very much depends on what the question is trying to test you on. So there are 3 fairly straightforward NMR spectra. Going to put some more on the board. See you in a sec. So just do a couple more off that environment list that we looked at. And we'll look at this, which is a different chemical to the ones from before. So here, the ethanol, that there is that one, that there is that one. How do you tell? Well, you get out the data booklet, and when you look at the carbon-13 NMR information, it says that the one that's attached to an O, which will go on to be the OH group of the alcohol, will be in a region that includes the number 56. And A is just an alkyl version, which is in a much lower ppm number, slightly higher energy. Same height because there's 1 carbon in each. This again, 2 peaks in the ethanoic acid, same height because there's only 1 carbon in each environment. Not marking the TMS off anymore, but you need to remember that the 0 marker is TMS, this is the 0. 21. Now which one will be that? Well, when you look in that data booklet, it says there's kind of, you know, the alkyl group. So that's A, which is the CH3 one. The carboxylic acid one, much larger ppm, energy lower to do the shift, 178, significantly higher. So yeah, 2 peaks, much further separated than that. So if you had, you know, a very simple question would be, here's 2, which one is an alcohol, which one is a carboxylic acid? That one's a carboxylic, and you can count the carbons and say which carboxylic acid it is, because it's got to be ethanoic acid, there's only 2 carbons. It's got to be ethanol, there's only 2 carbons. Now we come to this one here. This is not one of my ones from earlier. Right, this is an amine, where the amine is attached to the central carbon with 3 CH3s around it. And when you look at that, there are only 2 environments. The 3 CH3 ones are all identical. Think what that will mean for when I'm going to draw the spectrum. And then the central carbon, which is attached directly to the NH2, will be slightly more, well, unshielded, and therefore the energy will be slightly further to the left. So this one, so I'll call them A and B. This is the thing you need to get used to, is labelling what the carbons with a little letter and tracking it onto the NMR. So the one that, this is going to be B, that one's going to be A. How many carbons like A are there? 1. Remembering it's a very narrow pointed triangle, but I'm not going to do that. B, 3 carbons doing exactly the same. So that would be a nice 3 times taller P. And these ones are fairly far over compared to some of the ones here, like 18 and 21. That's because the NH3 group and what methyl groups do in molecules about donating electrons. So the spectrum would be a 3-to-1 ratio. So there we are. We're going to take an edit and we'll come back and do it differently. See you in a moment. So what we're going to do, slightly different, is that you, yes you, the watcher, are going to decide how many peaks there would be. I want to get a little bit more into it, you make some estimate of where on the ppm scale that peak would be. So you can predict two things.
Want to know the number?
And the position. The position will be a range. I'm not asking you, because you never get asked to say it will be exactly this value. That's not what happens at A level, it's not what happens anywhere, I shouldn't think. So you're asking, I'm being asked to do two things. I've got 4 chemicals that I want you to do that for, so just run through what they are. Methanol, see how many carbons, we're only talking carbon. Propan-1-ol, propan-2-ol, and then, well, I've not drawn that one out, you're going to have to do that yourself, 2,4-dimethyl pentane. So I'm going to ask you to pause the video, draw them out, identify, you're going to need the data booklet. If you don't have the data booklet, go to your exam board, get the data booklet. It's available in a number of other places. And then use that, they come little blocks of saying which chemical shifts will be representing what. So make those 2 predictions. I will pause the video because you need to pause it, and then we'll come back and tell you see if your answers were close to the actual ones. See them after you've had some working out. So, methanol, single peak, only 1 carbon, because we are doing carbon-13 NMR, I keep saying it because don't want you to get mixed up. And the actual spectrum has it pretty close to 50 ppm. Propan-1-ol, 3 peaks, all the same height, 1:1:1 ratio, because that's different to that to that. And these are the ppm values, 10, 26, and then this one here on with the OH is the 63. You didn't have to get 63, you just had to get it in that sort of area. If you don't get them exactly right, reflect on it. Think, oh, okay, need to be perhaps a little bit more lenient in my values or whatever. Propan-2-ol. Now there are only 2 peaks because this and this methyl group are in an identical environment and that central carbon different. So the 2 peaks, that will be 2 to 1 in peak height, and the ppms are 25 and 63, 63 being the one in the centre with the OH, so it's in that order of 2 to 1. I didn't say about the peak height, but you might like to have thought about that. And then when we get to 2,4-dimethyl pentane, 3 environments in 2,4-dimethyl pentane. Here they are labelled A, B and C. A is a single carbon doing that. B is that one where the branching takes place, and that's the same on either end of the molecule, left and right. And then the C represents the terminal CH3s, of which there are 4. So the ratios would be 1 to 2 to 4. Labelled A, B and C there. It is the most difficult one. And the values will be 49, probably the hardest one to get, 26 and 23. You didn't have to get those in the right order, you'd never be asked to do that, but the fact that you've said that they're perhaps in the 20s is probably a good thing, even 30s is fine. So there we are. We're going to again turn the tables and do it differently. We'll do what you're more likely to be asked to do. Here's a spectrum, what does it mean? But I need to clean the board and get it ready for that, so I'll see you after the edit. So here we are now doing, to be honest, what you're probably going to be doing in an exam question, which is you get given an NMR spectrum, probably more than one, to be honest. You probably get the carbon-13 one and the proton one, but obviously we're just looking at carbon-13 today. And it's not very complicated, just 2 lines on it. What's this line? You haven't forgotten, have you? No. Reference point, TMS. So when you look at that one and that one, that's twice the height of that one. immediately 2 plus 1 tells you there were 3 carbons in the compound. That's major things to do with what you say about the structure. You look up in the data sheet, and you'll need to maybe even pause the video at this point and look at the data sheet and go, what could 30 be? Find 30, look up across, vertically up, what boxes on that diagram does 30 go through? And it's a CH3 group attached to a carbonyl, CO. And I've written twice there because it's twice the height of the other one. The other one is 210, and that represents now it depends on your data sheet and which exam board you're talking about. Some of them say just C double bond oxygen, others go aldehyde or ketone, depends on your exam course which one you're doing. So summarising, 3 carbons. It's got to be aldehyde or ketone. That only leaves you with 2 choices. It's either going to be propanal or propanone. Here are propanal and propanone. Now when you look at propanal, there's the carbonyl one, which is going to be the one down the end, whatever. But that carbon and that carbon are not the same. That will have 3 environments and 3 peaks. The spectrum only has 2, so it isn't propanal, which means it must be this one. Why is it this one? Because that and that are carbon A, which represent that. And I strongly advise you to do this lettering and linking it to the peaks that you also label with the same letter and reference in your answer, because the way you have to do it, you have to write your thought processes down. So you would say A represents this, and there are 2 of them, and here they are in the molecule. And then this one is B, which is this one. So that is A, that is B, so all the letters match up. And that makes sense, because 2 A's, twice the height, a B, much further to the left, it's propanone. There we are. We'll do another one, but I'll need to get the board drawn, ready to do it. So I'll see you after the edit. So, slightly more complex now. Sample 2, 4 peaks, all the same height, meaning 4 carbon environments, none of them duplicated. The numbers are written underneath as 12, then 18, then 55, then 195. So letter them off A to D, analyse them A to D. A, 12 parts per million. It's going to be the CH3 attached to some other part of the molecule. B, slightly further over, happens to be that there, a CH2 group with normal carbon chain either side. This one here at 55 is a CH2 attached to a carbon with an oxygen. It can either be a single bonded or a double bonded oxygen. And then the 195, absolutely clearly plumb in the carbonyl. It could be an aldehyde or it could be a ketone. Now there is a way to determine by analysing the spectrum a little bit more which one is out of the 2, but at this point I think it's far enough to say it's going to be that or that. Butanal, butanone. Some people call that butan-2-one, but it doesn't need the 2. And so taking you through the analysis, you end up with, this is the type of compound, here's the breakdown of the carbon chain, not enough information. What really would happen is if you put that with a proton NMR, you will be able to tell which one of these 2 it was fairly straightforwardly. But we're not doing that yet. So that's example 2. We've got one more example to go. As you can see, I'm not being joined by any cute little assistants now because they've fallen asleep, as is the want of these little things. Little fluffy kittens that they are. I will see you for example 3. See you shortly. So our last and third example, here's the spectrum. Of course this is the 0 marker, we know what that's the TMS marker, and we don't need to include that in our analysis. A, B and C labelled up, and then we analyse A, B and C for what they are. 12 parts per million value, twice the height, so that's why there's times 2, so, or you probably need to say that represents 2 carbons. And the position of 12 is a CH3 attached to another carbon, so it's like a terminal CH3. And there are 2 of them. Now that immediately says that something, you've got some kind of symmetry in the molecule. But to get 2 identical carbons on the end must mean that the structure ends the same and is symmetrical towards the centre. And that has important implications for the structures that are drawn. Now, the second one, B32, represents a CH2 attached to a CH3. In this case, or well, we know it's that because how many carbons are there? 2 plus 2 plus 1 is 5. We know it's going to be pence in some form or another. And again, there are 2, so that again indicates that there is some form of symmetry going on when you look at the absorption of the radio frequencies at position B with 32 parts per million. And then there's only a single carbon doing C. It's 62. When you look at what 62 could be, it runs up through both the C to O and the C to N. Not a carbonyl. Carbonyl will be up near 200. So that means it's not an aldehyde or a ketone. That is likely to lead you to one of 2 things. Either an ether, which is not in many A-level courses, or an alcohol, which obviously are, or a C to N, which will be an amine of some form or another. Now, at that point, what do? You go, well, 2 identical, and a separate single one. You need to do this. So this here is the analysis, this is the analyse part. You then propose a structure. So you then go, what do I think it could be? It doesn't matter whether you get it right or wrong the first time. The thing you're trying to show in your answer is that you have analysed logically and worked your way through to an answer. So what you need to do is propose a structure. Now if you proposed the structure, let's say propan-2-ol, you would then draw propan-2-ol out. You can see that that is not propan. I didn't mean propan, pentan, because it's 5 carbons. Pentan-2-ol, and you would draw that out. You would then predict how many, what environments you got and where they would be, and you would go, that doesn't match because there's a wrong number of environments, because there would be. So then you go back round and you propose another structure, because what you do is you predict and you check that it agrees with what you've got. So you propose, predict, agree. If it doesn't agree, you go back and propose something obviously not massively different, and then run through the cycle again. And eventually out of it comes a structure where what you predict and what you analyse match, and therefore that's probably going to be one of the answers that's permitted. The answer to this one is you can't tell which of those 2 it is. It's either pentan-3-ol or pentyl-3-amine. However, they would both have that 62-ish is the area where you would find it. So in order to pin down what that is, there would be other things in the question. It might say that you could oxidise it with acidified dichromate, in which case it would be that, not that. It might say, well, you could have any number of other things. You might have some infrared spectroscopy where it has that rather than that absorption, or this would have a particular absorption that's nice and sharp, this one would be a big broad thing. There will be additional information that you feed into your discussion and you end up with an answer. It's quite hard to just have an NMR spectrum and that's all you get. You do get questions like that, but most of the time it's within a whole load of other information, and you do the detective work to piece together the evidence and a whole sequence of things, and out of it comes the answer. Because the question is almost always which chemical is it in some form or another the question is worded. So there we are. Now there are some, you would call them practice questions attached to this video, and then there'll be some answers attached as well. You need to have a go at them. Now I wanted to have two little fluffy beasts saying goodbye, but I've just looked down where they are down there, and they are underneath the sideboard, very much fast asleep. So I will say goodbye for them. See you soon. Bye bye.